In this problem, we're going to consider the piston-cylinder arrangement drawn for you in the problem. We have a piston, and inside this piston there is some kind of simple compressible system contained. We don't know very much more about it other than it is a blob of material in there. And we're told that it's compressed, or it's being held in this arrangement by a spring with a known spring constant, a linear spring constant. We're told the area of the piston head, and we're also told the atmospheric pressure. We're also given that at this initial configuration, state 1, the pressure is known. The pressure is 200 kPa, and the volume is 0.05 meters cubed. Heat is now going to be added. So there's heat addition. The symbol for heat is typically Q. And that's going to cause us to go to a new state, this heat addition. And you can imagine the additional heat will cause the blob to expand, and its final volume is twice its initial volume, we're told. So in order to really start off this problem, we need to draw. That's the typical first step. It's a way of organizing our information so that we know what we have, and we are able to know where we can go to get the things we're asked to look for. And in this case, we're asked to find a couple of things. We're asked to find the mass of the piston, this piston mass, and we're also asked to find the final pressure, which we don't know yet. So let's write down a governing equation or two. In this case, we're going to have a couple. The first step would be to reject the ideal gas law. We cannot use the ideal gas law in this problem, even though we have a pressure and a volume given. And the reason for that is that we don't know that this is a gas. So we can't use the ideal gas law unless we know what we're modeling is in fact a gas. This could be a liquid or a mixture of gas and liquid. Secondly, we don't know the substance. So even if we were to assume the ideal gas law, we'd have no way to get our ideal gas constant, which would depend on the substance in this case. So the ideal gas law is out, but we are asked to find some pressures, and we know that pressure is basically a force over an area. And we also know that forces, those are controlled, those are defined in some sense by Newton's second law. So the sum of the external forces to a system equals the time rate of change of the momentum of that system. And just like in class, we're going to assume that this goes to 0. That means that the forces are imbalanced throughout this process. What does that literally mean? It means that this is an idealization, because the only way that we would have motion is if there was a force imbalance. Well, we're assuming that they're always balanced, so what causes the motion? And we posited this mythical creature, the elf, that would kind of in a claymation stop motion, he's stepping in there every instant and changing things for us from outside, but he's not part of this system. So whenever we have the elf involved, we know that it's a reversible system, or a reversible process, excuse me, that every state is going to be a equilibrium state. So a reversible process is simply a continuous set of equilibrium states. So each one of these pressures and volumes in between 1 and 2, we're going to reach those in a balanced way, not due to a force imbalance. So this is our governing equation from last time, and in order to use it, we need to have a system. So in this case, the system that we're going to choose is the piston head, not the blob, but what the blob is pushing on. So in this case, the piston head, it has a number of forces at work on it. It has a spring force that's going to be pushing on it from this spring that's going to be compressed. It has an atmospheric pressure force. It has a force due to the gravity pulling on the mass of the piston head itself. And then lastly, this piston is really floating on the air blob. So there's going to be the pressure due to blob pushing up against that face. and all of those are going to be in balance. So the sum of the forces here is just the spring force, the atmospheric, the gravitational force, and the force of blob, and all of those are equal to 0. So in order to do this, notice that this is a summation, isn't it? It's a sum. That means always add. So the sign of these various forces that comes in through considering the components. So in order to do that, I need to draw some basis vectors. And we need to write down a constitutive equation for each one of these forces. So for instance, the force of the spring, you remember from physics, it looks like it's a restorative force. So some linear constant from Hooke's law multiplied by some displacement, let's call it y, since we're going to be displacing up and down here. And then we need a direction to add to this. And even more importantly, we need to define this coordinate y. In class, we defined the coordinate y to have its origin down here. That was because the spring force was 0 when, or the spring was unstretched, when the piston was all the way at the bottom of the cylinder. In this case, the spring force is 0, not down here, but at the initial location, state 1. So it makes sense that we would define y to go up, and that this line would be y equals 0. So when y is positive, that would correspond to the spring being compressed, y being positive, k being positive, but I want the spring force in such a case, when the spring is compressed, to be down. So the minus j hat direction is what I would assign to give this vector both its magnitude and its direction. Secondly, I'm going to have, or the force due to the atmosphere, P naught times A. That's also going to be in the minus j hat direction. I'm going to have the force due to gravity. That would be the mass of the piston times gravity in the minus j hat direction, down. And lastly, the force due to blob is just his pressure times the area that he's pushing on in the j hat direction. So this is the setup that I've got. Let's plug in these constitutive equations into my force balance, and I get in the j hat direction that minus ky minus p naught a minus mass of the piston times gravity plus p times a equals 0. So this makes sense. The pressure force due to the blob is being balanced by the gravitational effect and the atmospheric effect and the effect of the spring force. So this here is Newton's second law. It's always valid. It's simply followed directly from Newton's second law. It's just now rewritten in a way that really looks a little bit like an equation of state. I have the pressure here, which is a true variable. The pressure of my blob will change as I go from state 1 to state 2 as a function of, well, as I go from state 1 to state 2, the volume is going to increase, and so this height is going to change. Also here I have the spring constant known. All of these other constants are known except for this mass of the piston, which is not a variable, but is as of yet not known. So here we have the pressure as a function of y. That's what comes about from this expression here. Or we could have y as a function of pressure. In order to write this down in a more convenient terms of pressure as a function of volume, let's use some geometry. So from geometry, I'm going to have some area of the piston, and then I'll have some height that gets me up to the volume at state 1, and then from there I'm going to go up to the volume additionally added due to my increase in the y coordinate. So the total volume here, so I have this is like my volume 1, this is like the change in volume. What will that change in volume be? Well, it's going to be equal to the base times the height. So in this case, I'm going to have that the total volume is equal to the initial volume plus the base times the height. The total volume equals the initial volume. So volume is an extensive property, as we learned about in class. It means additive. And we really are interested in solving this for y and then substituting it into this equation. So I would have, instead of p as a function of y, I'd have p as a function of v. So v minus v1 over a is my height. So plugging this in, I have minus k v minus v1 over a minus p naught times a minus the mass of the piston, gravity, plus p times a equals 0. So this is still Newton's second law. But now what it's given us is the pressure as a function of volume. Now the new variable here, the new independent variable, will be volume. So what we probably want to do is consider that first, I've not assigned this p to be either P1 or P2 or any other p. It's good for all the states in between 1 and 2. Why? Because we assumed that this process was reversible, which means that Newton's second law tells me that the sum of the forces equals 0 at every state, 1, 2, and all the states in between, because a blob is what's causing this motion to occur, not a force imbalance. So how can we use this? Let's evaluate this at state 1 just to see what I'm talking about. So at state 1, all of these variables become their equivalent counterpart fixed at that state. So this is going to become v1 minus v1 over a. Of course, that is 0. And then I'll have p naught a minus mass of the piston, gravity, plus, and now P1 times A equals 0. So at the initial state, I have a mechanism by which atmosphere is forcing down on the piston head, and gravity is pulling down on the piston head, and the blob is pushing up on the piston head, but the spring force is precisely canceled at this point. It's 0. And happy day, I know everything in this equation except for the mass of the piston. So if I solve this for the mass of the piston, I bring it over to the other side of the equation, I'm going to get P1 minus P naught times A over G. Everything here is known, and I can easily compute that. We'll do it in a second. So if the mass of the piston is known, that means in this equation up here, everything except for P and V, which are both variables, are known. So let's now evaluate this at state 2. At state 2, I'm going to have minus k v2 minus v1 over a. So this would be like the new volume over the area. Minus p naught a minus the mass of the piston, gravity, plus p2 times a equals 0. Let's solve this for P2. So P2 in this case is going to be equal to P naught plus the mass of the piston, gravity, over area. And then have to divide through by A here. It's going to be plus K times quantity V2 minus V1 over A squared. Before we move further, just consider what happens when we plug in for the mass of the piston here. So if I plug in for the mass of the piston here times gravity over area, which is what this term is, I'm going to have P1 minus P naught. P1 minus P naught plus P, this just becomes P1 plus K V2 minus V1 on A squared. And that's quite easy to use. What's even more interesting is that this expression right here, I can easily write this down in general. In general, I would have that the pressure is a function of the volume, and it's just equal to P1 plus K times V minus V1 over A squared. So if I wanted to just draw quickly what this looks like in the PV plane, I can see that this is going to look like a line with a slope of K on A squared. And when V equals V1, this goes to 0, and P will be equal to P1, which is what I want. Also, I know that the slope of this line is such that the rise is K over the run A squared. And so this is kind of what I would expect the pressure to look like as a function. Because we also want to plot it. So you can also use MATLAB, of course. And let's go ahead and start up a new file. So VI homework, let's call it 1 problem 11.m. Clear, close all, CLC. It's going to be second nature to you very soon. And we go ahead and enter in some of our constants. So K is a 150 kilonewtons per meter. We've got P naught, which is 101 kPa. We've got our area, which is 0.25 meters squared. We've got P1 equal to 200 kPa. We've got V1 equal to 0.05 meters cubed. We know that V2 equals 2 times V1. That's going to be in meters cubed, of course. The next thing that we got to do here is solve for the mass of the piston. So the mass of the piston here, P1 minus P naught divided by, or times A divided by G. Now, this is when it can really pay to look at the units, okay? Our pressures here are going to be in terms of not pascals, but kilopascals. So if I have a kilopascal and I multiply it by an area, I don't get a newton, I get a kilonewton. And then if I divide that by G, which is meters per second squared, I'm not going to get out kilograms. I'm going to get kilograms times 1,000. So if I want this thing to be in terms of pascals, everything here will work out, right? 1,000, P1, P naught, if those are in pascals, then if I divide by A and G, I'm going to get out kilograms, which is what I want. So that's the first thing we got to do. The next thing we're going to do is we want to find P2. And at this point, let's go ahead and learn how to write a simple function in MATLAB. So up until now, we've used MATLAB really as nothing more than a tool that interpolates and graphs through interpolation. MATLAB is really powerful, and we can create functions using different files, but you can also create very simple one-line functions called anonymous functions that really help in terms of giving us some flexibility with using some of MATLAB's more powerful features later on without having to write too many files. So we're going to go ahead and make P a function. So the way we read this is that P is, the equal sign means is, and then the ampersand will mean a function. And then we need to say what it's going to be a function of. Well, P is a function of V, as we've written it. And that function looks like P1 plus K times V minus V1 all divided by A squared. So this right here is a pressure function, and the units of each one of these, let's check it out. The units of P1 are kilopascals. The units of K are kilonewtons. So a kilonewton. And what I really want to be able to do is multiply that by a meters cubed to get a kilopascal. So, I'm sorry, a kilonewton. And I want to be able to divide that by meters squared to get a kilopascal. So this is a volume. It's going to have units of meters cubed. And this is going to have units of meters to the fourth. So this is going to have units of 1 on meters. I already have kilonewtons per meter here. So this is going to be kilonewtons per meter squared, which is a kilopascal. So that's exactly what I want. And now we can use this to evaluate very simply what the pressure is at 2. So P2 is just going to be our pressure function evaluated at our volume 2. So let's go ahead and write this. And run it. Oh, we forgot to define something. It tells us right away we need to define G for this to work. So let's go up to the top. G equals 9.81 meters per second squared. I'll run it one more time. And now we're told that the pressure is 320 and that the mass is quite high, 2,522 kilograms. So that's almost everything we need to finish this problem. The last step is that we are asked to really plot this for all of our volumes in between 1 and 2. So let's do that. How can we do that? Well, let's set up an array of volumes. We'll call it V. And we'll set that array to go between the initial volume and the final volume. And let's put, really we only need 2 points. It's going to be a straight line. We've already kind of figured that out. And then we also want to have an array of pressures. We can do that in a number of ways. We can either set up a new variable called P vector, say you can call it P as a function of V. That might work. It will work. In this case, it will work because even though V is a vector, it's just ever multiplying or being divided by scalars, so that's just fine. And then we can plot it. V as a function of and PV and X label. And these are going to be volumes in meters cubed. And Y label pressures in kPa. Pressure of blob is equilibrium thermodynamic pressure. Let's run it. And what do we have here? The volumes seem to look hunky-dory, but our pressures are having some trouble. Let's look at our pressure vector. So it says it's 200 in both places. Oh, and that's because I didn't write V2 here. I wrote V1. And let's take a look here. So my initial pressure is 200 kPa, just like I anticipate, at a volume of 0.05 meters cubed. The final volume is twice that, so 1 meter cubed. And the new pressure at that point is 320 kPa. And that's how we do this problem. So we would print this out and turn it in.